Alright class, today we'll use ANSYS Workbench to work on thermal analysis problem. So the problem we deal with is heat sink. So with the geometry and shown in this slide, the material we use aluminum. So thermal conductivity, heat capacity, density, Young's modulus, Poisson ratio, and thermal expansion coefficient are provided. So the problem will ask us to do three kind of analysis. The first one is steady state thermal analysis. So with the condition, boundary condition, we have a constant heat flux go to the bottom of the heat sink, and at other surfaces is connected with the air. So the ambient temperature of air is 28 Celsius degree. So there is a heat transfer coefficient of air because of a convection. H is a 30 watt per unit square and per unit degree. Okay, that is steady state thermal analysis. And the second question is we change the constant heat flux into a square wave heat flux, and then the heat flux will change with time. So 45 second 0, and then jump to 1000, and then come back to 0, and then jump to 1000. Well, you can imagine that the temperature will change with time, so the boundary condition will still keep the same, and the problem is look at the temperature and heat flux change with time. So this is a transient problem. And last, the third question is to do a thermal stress analysis based on steady state solution. So after steady state solution, the temperature will have a temperature distribution, and the temperature will cause a thermal expansion of this material. And the problem is calculates the thermal stress and deformation. Okay, so with this in mind, with this information in mind, we'll jump to Workbench to work on the project. So we first look at the first question, which is a steady state thermal analysis. So we can choose steady state thermal analysis, and here we'll go to engineer data, where we'll generate a material that's called aluminum. And for this material, for thermal steady state thermal analysis, we only need one parameter, which is the thermal conductivity of the material, which is 170. So let's choose this value, and then after that we can close it, and we go to geometry, double click on geometry, make sure that the 3D type and solid bodies have been checked. Alright, now we are in space claim. So what we'll do is we select a new sketch surface, use the plan view, and then we'll check whether the unit is millimeter, because we want to use millimeter unit. And now it's a millimeter, it's good. Precision 2 is good. Minor grid spacing is 1, good. Okay, click OK, and then we start our sketching. So because it's symmetrical along y coordinate, so what we can do is we can first draw a construction line, which is to help us to image one half to the other half plane. Okay, so we draw a line. It can be any length, but it should be on y coordinate. And then right click on the construction line, set as mirror line, and then what you draw on one half will automatically project to the other half plane. So we'll start from here, and we start from the origin, and then draw 11 millimeter and then draw up by 3 millimeter, and then go back by 3 millimeter, and then go up by 1 millimeter width, and then go down by millimeter, and then with 2 millimeter gap, and then go up again 8 millimeter. Make sure that is 90 degrees, so 1 millimeter, come down, and then 2 millimeter, 8, 1, come down. Okay, and then go to the Y axis and press escape on the keyboard twice, and then you are in select mode. So, and then click pull, and then we'll to pull into 3D. So what we'll do is pull the surface. Oh no, that's not what we want to do. About this, Control Z. We'll pull this surface 15. All right, and then we have this solid. Okay, so now you can move. We can delete this curve. We don't need it anymore. All right, now we have this geometry, and then we'll close it. We'll go to the model. Double click on the model, where we'll do first to work on the first problem, which is steady state thermal analysis. Well, the boundary condition, so before going to it, we have two boundary conditions. One is at the bottom, there's a constant heat flux going to it, and other surface is contact with air, and which the air will carry the heat out, and the temperature air is 28, and the convection heat transfer due to convection of air is with the parameter H is 30. That's a review of the boundary condition. So when it's loading the geometry, let's review the boundary condition again. Steady state thermal analysis, at bottom heat flux going to it, and get out through air. Okay, so now we go to the geometry, look at solid. The first thing is to assign the material. So by default, the structural steel, we don't want to use structural steel, it's aluminum, which we have created. Okay, and then we go to mesh. Here we'll insert size, and we'll choose the whole body, apply, and element size, let's go with 0.5 millimeter, and then mesh it. Okay, so now we get this mesh size, and the size of mesh looks good. After that, we insert two boundary conditions. The first boundary condition is heat flux from the bottom. So not heat flow, okay? It's a heat flux. The difference between heat flow and heat flux is well, the units are different. Okay, the heat flux is watt per or power per unit area, or in terms of SI unit is watt per unit meter square, where we'll apply the heat flux to the bottom. So let's use surface filter, apply, change this value to 1000. Okay, and then insert the second boundary condition, which is a convection. So the air will carry the heat flux away, and the geometry will apply is all other surfaces. So we need use surface filter and click all the surface. Control select all the surfaces. Okay, we'll go to other perspective, make sure that all the surfaces will be selected. And then you move around, make sure that all the surfaces except the bottom have been selected. If you are right, if it's right, it should be 29 faces. Okay, and then click apply, where we input the convection heat transfer coefficient is 30. Ambient temperature is 28. Okay, after that, we look at the output. We want to look at the temperature, and we want to look at the heat flux. So after that, click solve, and we'll solve the problem. Let's look at temperature. Okay, that's the temperature distribution. And if you look at the temperature scale bar, so the temperature at bottom is a little bit higher than the temperature on top, but most of it's very close to 33 Celsius. And this is a heat flux, and heat flux is a vector, so you can click vector format and zoom in. You can see that how the heat goes from the bottom all the way to the heat sink and go to the air. Okay, now we finished the first problem, and then we'll work on the second one. On the second one, which is a transient thermal analysis, and with the initial condition that the provided by this temperature distribution. We'll use this temperature distribution as initial value for the transient analysis. So to use the result of statistical thermal analysis, so let's first close that. We can start from, based on the statistical thermal analysis, we can put another analysis, transient thermal analysis here. Choose transient thermal analysis, move it to the solution. So that means transient thermal analysis will pick up the solution of static thermal analysis and initial condition. So move to the solution and release, and that's what we have. Okay, so but for the transient thermal analysis, as we have discussed in class, we need more information, a thermal coefficient information about this material. So we can click aluminum, we need to put more information about that. Aluminum, we'll go to the density, so increase the density, which is 28,000. And then after that, we need specific heat, which is also showed in the thermal region. Click on it, where the value is 870. The unit is joule, per unit kilogram, and per unit Celsius or Kelvin degree. So, and that's all the information we need to solve the problem, and then we can close it. And then we can go to the transient thermal analysis setup. So double click on the setup. So upstream data need to be reread. Click yes. Now when it's loading the result, we have a review of the second problem where we'll use time heat flux into the bottom, and we'll change with time. It's a square wave heat flux. So that means we'll change the boundary condition to a square wave heat flux. Right, now we are here, and then what we'll do is we click on the transient thermal, insert boundary condition. We have two boundary conditions for transient thermal analysis. The first one is convection against this will apply to all the surfaces except the bottom. Do this again. Recall that there will be 29 surfaces, so more around. So when there are 29 surfaces selected, that means you're right. And then apply. 30 for film coefficient, ambient temperature 29. Okay, and then after that, click on solution, where we'll insert temperature and insert total heat flux. And then we can do the calculation. Oh, I forget that another boundary condition here. Another boundary condition is the square wave heat flux. The heat flux, which will apply to the bottom. Well, this heat flux will change with time. It's not a constant value anymore. So to do that, we need to change this to tabular. The magnitude is a tabular change with time, right? And then you click on tabular. So here we can make a tabular square wave function, which okay, before input the time, we also need to set the simulation time. Okay, so that we want to set the total simulation time was 180. So once you set to 180, then we can extend the square wave input time to 180 seconds. And you can also change the initial time step, minimum time step as maximum time step. Okay, so we can set it auto time stepping as program controlled on, so which you can control by ourselves. Because this is square wave is a square wave input. It have a sudden jump of temperature, and we need a smaller initial time step. But we will see that later if we don't change it. Right, and then let's finish this. Go to the tabular data, and we start from 0. And we put one more data. 145 is still 0, and then 40.1, which has 1000, jump to 1000, and then 90 1000, and then 135. Oh, let's go to 90.1. little bit larger and then become 0, and then 135 is still 0, and then 135.1 it come back to 1000 again, and then 180 1000. Now we have this tabular square wave shape, and then we have the heat flux. After that, we can solve the problem. So if you'll see the initial time increment may be too large, the reason is because it's a square wave function and the input has a sudden jump in value. So, well, as a result, it'll give you a warning. So what you can do is to eliminate the warning is here you can change the initial time step to a smaller value. And to do that, you need to change this auto time stepping to manual, not program controlled. So you can set it on and then solve it. But anyway, let's look at the result. Okay, that's the result we get. This is a total flux. This is a temperature. You can have a look at how the temperature change with time. Okay, temperature, how the temperature change with time. And the x-axis is time from 0 to 180, and then you have temperature. Okay, and then here's a heat flux. Here's a how you can change the initial time and to eliminate the warning. So you can set the initial time here. If you set it auto time stepping as on, and then you can set your initial time and the minimum time step. Well, let's come back to program control. Alright, that's the result we have for temperature and total heat flux. And you can also again see how the temperature change with time, because this is a transient problem. Okay, so now that's answer to the second question, and now we'll go to the third question, which is to do a thermal stress analysis based on steady state solution at the temperature load. Okay, and the boundary condition again is the base of the heat sink is fixed. All right, and then we'll go to do the structural analysis. We'll use static structural analysis and move to the solution again. We'll use the solution of static state thermal analysis result, and which will lead to the third project here. And well, to do that, we need to put more information to the material. Where is it? Yeah, so click on the material field variables, and what we'll look at is thermal expansion. Linear. Oh, here you go. So we need to find isotropic instantaneous coefficient. Click on this. Okay, so that's where you can put is thermal expansion coefficient. So the value provided is, let me look at that, 22 to minus 6. Okay, minus 6. And input again, or 2.2 10 to minus 5. Okay, that's the value we have. And then you can close it and then open double click the setup and then open the mechanical modeler. Click yes. And this will allow us to do a thermal stress analysis based on the temperature distribution obtained from the steady status thermal result. And the last question is quite simple because the boundary condition is a very simple boundary condition. So insert fixed support. The fixed support will go to the bottom, apply, and then you can insert deformation to the solution, and then insert stress to the solution, and then you can solve it. Oh, it said that there's something wrong with the material property we set. Let's look at the property we set is density. Oh, we forget about this Young's modulus of Poisson ratio. Let's go there, go back to our engineering data, and here we forget to add elasticity to the material, which has a Young's modulus (10) 7 to 10, Poisson ratio 0.3. Okay, and then make an update. Okay, now we have Young's modulus Poisson ratio, and then we can run the simulation again and solve it. Alright, now we have the total deformation and stress distribution. This is stress distribution, this total deformation, and this is a deformation due to the thermal stress, and this is the thermal stress level. Okay, so that's all we have for this problem, and I hope you can enjoy it.